Welcome to qnawire.
Okay, so the question asks, at room temperature, what is the strength of the electric field in a 12-gauge copper wire with the diameter 2.05 millimeters that's needed to cause a 4.5 amp current to flow? And what would the field be needed if the wire made of silver instead? So to answer this question, we want to look to equation 25.5, which tells you that the resistivity of a material is equal to the electric field divided by the current density. So looking at that, we have the resistivity and we have the current density. And so we can use this formula to solve for the electric field. So I'm just going to go ahead and write that equation. And then this is the magnitude of the electric field. So I'm not going to worry about vector signs. So it's rho times J. And so current density is the current per unit area flowing through a cross-sectional area of the wire. So I'll draw a little picture in a moment, but first I'm just going to write it as current divided by area. And now I'll draw a little picture to explain better what I mean. So if this is the wire, has some radius R, and then it has some area A, and then like kind of the currents flowing this way. Okay, so now let's go ahead and write out what the area, the cross-sectional area is, and then we can take that and plug it into the electric field formula. So, oops, go back. Okay. So the cross-sectional area is a circle, so it's just pi r squared. And we're given the diameter, so we need to half it to get the radius. So it should be pi times 1.025. Oh no, wrong way. Let me retype that. A equals pi times r squared equals pi times 1.025, and then it's millimeters, so we need to convert it to meters because I just want to use SI units for the problem. And so to ensure that the electric field is coming out of proper units. So in SI units. So yeah, so that's how many meters there are. In the radius, 1.025 times 10 to the minus 3. And so that's our formula for the area. And I'm going to go ahead and calculate what that is. So pi times 1.025 times 10 to the minus 3. So that's equals 3.3 times 10 to the minus 6 meters squared. Oh yeah, and I'll go ahead and put meters in my units for the area. Okay, great. So now we kind of have all our ingredients prepared, and I'm just going to go ahead and plug it into this formula for the electric field. I'll type out the numbers that I'm using. So so I need the resistivity of the material you can find in table 25.1. So it's copper, so that's 1.72 times 10 to the minus 8. And then I is 4. Oh my gosh, every time. Okay, I'm going to rewrite this. E equals 1.72 times 10 to the minus 8 times 4.5 amps divided by 3.3 times 10 to the minus 6. I'll go ahead and stick in all my units. Hopefully I can move this text box. So yeah, no, it just disappears. Okay. I'm not sure exactly what I did. It's something to do with deleting. So E equals 1.72 times 10 to the minus 8 meter times 4.5 amps divided by 3.3 times 10 to the minus 6 meters. Okay, I have no idea how to actually delete things on here. Is it, I guess if I press it twice, the box goes away. So I can't press delete twice. Okay. Great. So I'm going to go ahead and type that into a calculator. And I got 0.023 volts per meter. And that, so that's pretty similar in magnitude to the number that was obtained in a example in the book. So that would be example 25.2. Okay, and so yeah, so that's part A, and I'll just like label it as part A. And then now I'll do part B. So part B, you change the material, so that just means that you're going to change this row value from 1.72 times 10 to the minus 8 to the value for silver from that table. So that's 1.47 times 10 to the minus 8. So I'm just going to copy this. Oh, and I'll add, oh my God, please don't delete. And I'm going to add a subscript for copper. Okay. And yes, you can move it. So I'll move it somewhere slightly less in the way. Okay. Okay. And you copy and paste these boxes. I guess not. So I guess I'll type that out again. E silver equals 1.47 times 10 to the minus 8 meters times 4.5 amps divided by same number, 3.3 times 10 to the minus 6 meters squared. I suppose I could have just copied the text. Okay, and then if you put that into a calculator, oh, I'm going to edit this to make it say copper. Okay, if you put that into a calculator, you get .020. per meter. And so just some comments. I knew the units were volts per meter because that's a SI unit for electric field, although it doesn't pop out of the equation. I suppose ohms times amps gives you volts. And then the meters cancel, so the units all work out. And so this is telling us that silver is a better conductor because you only have to apply 0.02 volts per meter to get the same current that you would need to apply in copper, whereas in copper we'd have to apply 0.023. And I think that's it.